We'll start now.
Yes, sir.
I will start now. Let others join. Okay, so last class we have seen the numerical integration of various methods, which includes the left sum, right sum, middle sum, and then we have seen the trapezoidal, Simpson rule. Okay, there are various methods we have seen. In addition to that, there are three more important methods, which is using the special function. So by learning this numerical integration with the special function, we learn something about the special function also, some of the interesting aspects about the special function. So this is the Gaussian quadrature or a Gaussian Legendre function where you can use the numerical integrations can be performed for some special kind of functions. And here you have a limit a to b f of x dx can be written as this. AI, which is the sort of coefficients from the Legendre polynomial, which you get it, and then roots are f of x sine, and substitute that into the your function. Use the corresponding weight function or the coefficient, which can be used from the Legendre, and it happens to be Legendre differential equation solution. So therefore, it is named as Legendre, Gauss-Legendre method. And you are all familiar with this Legendre polynomial special function you must have studied. 1 minus x square d square y by dx square minus 2x dy by dx plus n into n plus 1 into y equal to 0. And this has a solution with the Legendre polynomial of given n. And you have a large number of solutions that are available. For every n, there is going to be a solution to this equation, which we can check it here for a simple case. Take this as a Legendre differential equation, which is mentioned here. You can here y double prime, y prime is here, and y, which is y of x. So what I'm going to do now, I'm going to take this y from the Legendre polynomial p n comma x, and then the derivative also has been taken with the differential d with respect to the x, and here again do it twice. Second derivative also has been found. So this Legendre p of n of x is already available in Mathematica. It's all well established, well defined as a Legendre polynomial in the Mathematica itself. And any value given n, you will get the polynomial Legendre polynomial for a given n that is possible. So if you wanted to see that, probably it can be generated here for a while. No, I think it's already given here. You can see here, Legendre NP of 6 has been plotted here from n varying from 1 to 4, which means if I take out this, enter here, I'll get the, so something has been, so this is the n equal to 1, this is polynomial n equal to 2, 3, and 4. You can have any number which you like. Okay. So those solutions are substituted this differential equation. They are all solution to this differential equation. That's why they are all special functions. Okay, the solutions are special functions, and they are named after the person who discovered this Legendre P, the Legendre polynomial. This is discovered by Legendre, and it is being substituted here and checked for up to 5. I have written solution n, the delayed equation form, which is defined, wherein it evaluates the solution. Okay. Then it takes the first derivative, second derivative, function also substitutes and checks. So you can check whether they are all solution to this differential equation or not. That can be done. In fact, this program I have written 2003. Okay, it's quite old program which I have written. I think if you wanted to check the date, this is modified now. Okay, I just modified. You can check here. This is numerical method. In 2003, at that time I have written. You can see I just modified now. 2003, all the programs. And this also has been written at that time. Now it can be modified and it can be much more effectively one can write. You don't have to write so many number of lines also. But anyway, we can have the complete details about it. So by the process, you will learn about what is the special function of this legendary polynomial and what is the corresponding differential equation and its solutions. And you are going to find the roots of this legendary polynomial. That is what your x of I. Okay, that can also be found simultaneously. Okay. Now I have defined this solution. Substitute first for n equal to 1. Okay, it substitutes and it evaluates all these values for n equal to n equal to 10. So you have the result for up to n varying from 1 to 6 which you have found. It doesn't look like it is satisfying, but this is as it is results have been given. You simplify that. See, it is a solution to this differential equation. Okay, it goes to 0 and therefore it is going to be this equation is satisfied with the solutions what you have. So simplify goes to 0. That this is the output which you have taken here. Or you can, as I said, put a backslash, it will become an input and then you simplify it. It goes to 0. So we have confirmed that these are all the solution to this legendary polynomial and this is the differential equation corresponding. There are so many properties are there. So before that, we just first complete the integration part of it and then see some of the properties which we are already familiar. Okay, this is the polynomial. Now this is the plots for a few of them. And you can go ahead with the large number of plots also. Okay, I have made a table of that function. See, this is the table of the function. At that time, I can have any number of polynomials. I can plot it. See, for example, I can have a 10 polynomials at a time table, and then all the 10 has been plotted here. Okay, you have all the 10s, but it looks very clumsy. So you can start from 5 to 10 and then look at it also. This is 5 to 10. Okay, this is somewhere 8 to 8, 9, 10. 3 of them are there. Like that, it's possible for us to see how does this function vary. And you can look at the limits of this. Somewhere -1 to +1 we have plotted. Suppose if I go beyond this, what is going to happen? Two. See what is happening? Any idea what is going to happen when it is close to or greater than 1? Let me take 1.1. Then we have 1.1. Started shooting up. 1.5 to 1.5. Oh, it's already become huge. And if you ask to plot range all, plot range all, it's already come to up to 3000. If I make it 2, say you lose all information that is happening at small values, even by x equal to. So by the time it becomes x -2 to +2, magnitude has become enormous. Okay, it's 10 power 5 by the time it reaches 2. So it has more information within +1 to -1. And we can have the plots starting from 0 to, so let me take 5 of them. This is what the just that you have for the legendary polynomial. Okay, these are all polynomials and they all have a roots. Equal to 0, find out what are the values of it that goes to 0. That is what the roots of this polynomial. You get the point? I expect 2 roots here, I expect 4 roots or 3 roots here, there is a 4 roots are possible. All this information that can be pulled out, because what do you mean by the root? For example, if you take this, let me take one by one plot style. Okay, because I want to distinguish one from the other. So I'll make first is red, and copy this and paste over here. You can use different symbol also if you want. Make it a second one is blue. I'm differentiating this in colors. Third one is green. Fourth one as magenta. Okay, I have 4 different colors now. What happened? All of them are showing is the same color. It's just taken only the red. So what should we do? So we will add, evaluate, gas. We will evaluate one by one. Then see what is happening. No, that's only one I've given. Evaluate. Table. It should be closed here. Text given only one. Okay, we'll try here. Because we want to distinguish from one to the other curves. I'm just looking for the possibility of getting different colors. Okay, I'm able to get it now. Evaluate, and it gives, I think there is no control over that. It has taken its own color and it has given. So evaluate, it gives this. You can see here. No, magenta is somewhere else. So I think you should find a way to get the colors. And I believe that if you look at carefully, for example, this one, fourth one, it must be crossing this axis 4 different places, so that it has a 4 different routes. 1, 2, 0, 3, and 4. Okay, 0 obvious for this. So therefore 4 routes are possible in addition to 0. Okay, so that's this problem of getting a plot style, evaluate, position to locate them. Sometimes these simple things creates a problem. Yeah, I'm able to get it. Because I made it independent plots, it has not been accepted. So now you can see this red one, then blue is there, green, and how many are there? So 1 to 5. You have 5 of them. 1, 2, 3, 4 only I have. I need to have one more. Purple. Yeah, now we can see. All the different colors you have, and the distinguish from one from the other, and they are all crossing over that. Therefore, every time you find there's going to be the zeros are available depending on the magnitude of the n. Okay, these zeros are being used for the value of xi. That is the idea here. Okay, so you can see I'm writing this n sol. Numerically, you solve this for xk, that is suffixing, that is different roots that are represented by xk's. And for example, for n equal to 16, you find out all of them and get that roots and then use that to find out the value of AK, okay, which is the AK is something like, this is the AK, AI is the AK here. You can rewrite it also, that's not a problem. That is given by this expression, which is already established to find out the value of AK, and the roots also found. Now you write both the root R of RT of I and this AK values, corresponding AK values, and make a list depending on the n. So this is available for you. You can see this is the output which is created and it is being tabulated. You can, if you want, you can change the numbers n. So if I change the number n, let me start from 6 somewhere. 6 till the 6th order polynomial that will be considered. They have 6 only. You can see there are 6 roots corresponding to this AK has been found. That is the number. And this will go into your computation for finding the numerical integration of the given function. Okay. So that's the idea here now. So we need to have the AI and the XI. That is the thing that should be generated before you start the computation. So when I use this photon, what we do, we will read these parameters, referring from the standard tables, take out these numbers because we cannot, it will take too much of time with that. Of course, nowadays they're able to build in the photon also, you can find the roots and then take and use it. Here it will be much easier now. Just solve that, get it, take out, put it, then look for the solutions or do the numerical integrations. Now I am going to take 10 of them. So if you want to have the 10, just shift enter, shift enter, shift enter. The AK can also be found, tabulate it. I have 10th polynomial, 10 roots and the corresponding AIs that has been found. Then that will go into the computation. So we have here we have taken 16 or a 15, 16. Let me take again. AK and 16 are available, and we are going to use this. So now this is being integrated as it is by using the Mathematica statements, and numerically we have evaluated 1/4 of pi sine 1/4 of pi 1 plus x, and that has been integrated from -1 to +1. Okay, the definite integral. Chop means if it is a small 10 to minus above 10 to minus 16, it will be taken as 0. So that's if necessary, you can use it, otherwise you don't have to worry. In fact, these three, if you remove, I don't think you have any problem in getting this result. You have it. Okay, that's all not necessary now. So -1 to +1, 1/4 pi sine of 1/4 pi 1 plus x equal to 1. Okay, now I'm going to use this A of I. You have to sum over it. From I1 to now n is taken as 16. Okay. Then you replace this x by the root what you have found, that is your x now. That is substituted here. That's all. You have a result now. So you can see what would happen to the, suppose I try with the 6 itself, could be possible to get it because integral is quite simple. So therefore, sum will be automatically be taken care, because I1 to n is going to be 6 already, which is defined here. N is 6. Therefore, that will be taken care, and you would get this result 1 already. You are getting it. Even for a 4 or a 3 also it's possible because of the nature of the polynomial. Let me try with the 3 roots have been considered. What happened? I do not know. This one of them is 0 in this side. have to cross check it. Anyway, we'll check it. And this must be less than. See, the error is only at the fourth digits and fifth decimal and decimal, and we have a error. And this is enough. So we don't have to go for a 16 terms. So maybe 4 if you make it, probably you have a solution for that integration. Now, this is actual integration and this is the calculation. So 4 steps are enough. Next integral is cos of x divided by 1 plus x. Please note that you have to make this transformation of the limits. Why? Because this is limited to this a and b, whatever be the value that you have. If I make this transformation, it will be automatically the limits goes to -1 to +1. Okay, so therefore this transformation, if you may carry it out for any given value of the integrand with the x variation, then if I have the b and a as it is, if you take it to the integral, then you can substitute as it is a equal to 0 and b equal to pi by 2, which is equivalent to converting this lower limit and upper limit to -1 to +1. That is the purpose of this variation. Okay, x you make this transformation, which automatically converts the lower limit upper limit to -1 to +1. Okay, and make a substitution, and it will be getting the result. So my x is converted in this form with this transformation that can be seen here, u here, and I will take this. Okay, that's what is being replaced. X is replaced by x of rt. That's the solution to that, and that's substituted here. And a with the b minus a by 2, that's also additional term that will come because of this transformation. Okay, that transformation you carry out, and then substitute the a equal to 0, b equal to pi by 2 with this transformation. This is converted to -1 to +1, this integral of this. When you have -1 to +1, replace that weight, the so-called ai's and the xi can be substituted correspondingly. So that has been shown here for you for a clarity purpose. Okay, numerical integrated, you have this and substitute that and simplify. You have a 6.26.6736.149, and maybe you can have a larger integers here. And then check now. 66736. Instead of 2, 1, I have something else because I have limited to 4 only. So I'll increase this number to, say, let me take about 8. Okay, so this is the root of the 8th polynomial, and that weight function which comes and sits here. Now I can check whether this is going to improve or not. It should, whether it should improve. It is, right? It's improved now. I mean, if you put it in a number form, this must be having a bigger number, and then that can be also be compared. So depending on the integral number of terms correspondingly, you can increase it and make sure that you are having a required digits of accuracy. Next is 0 to pi by 2 log of 1 plus t dt. This is the actual integration. It's the number that you have that has been shown here, and we'll check for the number of, I think we have used the polynomial, legendary polynomial order 8. With that, just make a change here and then substitute and confirm it. That's right. With this, you are able to get the accuracy what has been given in 0.85658, 659 you have. Maybe you can improve a little more with this 10 number of the 10th polynomial, find out its root and corresponding ai, which we call it as a weight function. So this legendary polynomial, and we just check whether this is going to be better now. Should be, yes, 58991. It's better. Okay, so this is how we will be performing the integration by using the legendary polynomial. So you find out the weight function for the legendary that is being obtained by the function which is being defined like this. I think there are 2-3 ways it has been given. This is one of the ways which can be used for the weight function. Evaluate this. Okay. Then with this weight function with the corresponding polynomial, substitute it and simplify. You have the results, which is the idea now. This is the Legendre polynomial. This is the generating function. You can generate and compare with the polynomial what you have with this Legendre polynomial. Orthogonal properties. You can see here k and n. When k not equal to n, you have a 0. When k equal to n, you have the finite value, square of that. And of course, x power k with the Legendre polynomial, these are the results that you will get for different values of polynomial with the corresponding k values. Okay, 3 is the x cube of this integration. This is Rodriguez's formula here. Okay, this is the equation which is satisfying for different n's. For example, n equal to 1 to 5. We have shown it is true, both left hand side equal to right hand side, therefore it is satisfying. And of course, we can start from this x power n, we can have a, this is also possible. Okay, this is another way to write x power n of Legendre polynomial. This is with generating function, this is with the Legendre polynomial itself, and these are, they are one and the same. These are all the things which is there in the textbooks. These are well known about this Legendre polynomial. And this recurrence relations again. N plus 1 of Legendre equal to 2n plus 1 minus n Legendre n minus 1. This is alternate way of getting that. That's also, that's fine. Now we can see all about the Legendre differential equation and the polynomial and its properties, and that property, one of the interesting aspects of that is being used here to evaluate the integrals of particular type, which is given here now, where we try to convert the limits by using this transformation. Using this transformation, convert to -1 to +1 and perform the integration. So it's quite interesting to see. We are able to learn a little on this Legendre polynomial. Where do you come across these Legendre polynomials? Anywhere else? In your physical problems? Any idea? Legendre P? No? Is there any way? Anywhere? Did you see this Legendre polynomial anywhere else in your physics problems? Physics text or physics chapter, physics subjects? Legendre polynomial.
Hydrogen atom.
Quantum
Yes.
mechanics, sir.
Quantum mechanics, hydrogen atom. What is the hydrogen atom does? When you have an orbital angular momentum, Legendre polynomial. If you include the spin, it will become associated Legendre polynomial. Okay, that's this one level high. You have to add that you will be looking this equation. This is L into L plus 1. Okay, so you have the associated Legendre and the Legendre polynomial. That is your part of your spherical harmonics orbits. Okay, so and here your weight function is e power. I believe it must be e power minus x. No, that is for logger. Here the weight function is 1 or something else. I don't know, but exactly what could be the weight function for a polynomial part. I don't think you have any weight function here. But there you have a logger and Hermite have a weight functions. Okay, so this is all about the Legendre and Legendre polynomial. All its property you can like this. You take a Orphan mathematical physics. They're all familiar. Okay, you have this Legendre polynomial and Legendre given. What are the textbook results? Whatever he has given, all can be proved simply by solving like this and get to know about it, about all these properties of this Legendre polynomial. Not at all difficult. And by the process, you will understand what is this actually special about this integration or this differential equation. Okay, something special. So that's why this is become a special function. So this has some speciality. This again a second order differential equation, but it's a special kind. So that gives this legendary polynomial. And there are multiple roots. Okay, what is it actually meaning of that? Okay, and this has been discovered about 350 years back, and that is being exploited for studying the hydrogen atom last century. Okay, so you can see beauty of this mathematics has been found long back, but that has been explored by a physicist extensively during the last century. So much has been done, and so much has been used to understand about the atomic and subatomic particles. Okay, that's how they become so important now, and we have a lot of other applications of this legendary polynomials. Okay, it's quite interesting to learn about this kind of a differential equation and their solutions. So this is one such type. So anything you wanted to clarify here? I'll go to the next one. This has been done in the numerical methods, Shaheen. Govindaraj. Have you done this in your numerical methods? No? Anyway, okay. So I just save this and come out and then look into this second aspect of second
So we
part.
have done Gauss legend, minus half to plus half.
Minus half to?
Plus half, we translate the integral limit to minus half to plus half.
No, the same only. This is also same.
Yeah.
It can be written as -1 to +1 also. Okay, so it's not a. You might have done specific with the specific value some cases. It's not some specific function.
Yes, sir.
They see when you use legender means it is actually a Gaussian-Gottreger type. Gottreger which uses the legender. So that's what the meaning of that. Okay, and see, in fact, the transformation I have not even converted to show that integral -1 to +1. The transformation as it is, you take it to the integrand itself and make a substitution as it is A and B. Is that right? You see what the way in which I have done? I have not converted the integrand, okay, with the limits -1 to +1 by substituting and then making the variables to the x-axis and y-axis. I'm sorry, this is lower limit and upper limit. Retain as it is and then make a substitution in the place of x's. That's all. Follow what I'm trying to say? I think that goes directly there. No, why should we? See, we need not write. See, for example, first integral. What I have done is, this is being generated automatically. I'll show you what is this first part of it. You can see here. This is -1 to +1. Okay, no transformation. If you bring all other things also -1 to +1 by making the variation on the variables, it will be of the form -1 to +1. Okay, instead of A and B, okay, here integration, I am just retaining as it is with just my substituting this. If you bring x into this form, automatically that will be taken care to get this in the form of -1 to +1 limit. That's what it means. You don't have to bring it in the explicitly and then make the changes in the variables, which is automatic. That's the reason why I'm not shown it. Of this integrand with the limits -1 to +1, you don't have to struggle because that will be taken care automatically by substituting this A and B as 0, B, because this substitution takes care of converting the limits into -1 to +1. Okay, this has been retained in the functions with the changes that has been accommodated because I am replacing x by this. Okay, you follow?
Yes, sir. By converting that, the limit, the function will
function will transfer to other variable.
-1 to +1.
This becomes u variable du. Integral u du form it will be get converted, and the limit become -1 to +1. That's what it means. Follow?
Yes, sir.
See, this is the transformation. And if you make all the variables into u, the limit will also becomes -1 to +1. Instead of that, I just substitute in the x with the whatever change which I am going to make, okay, the corresponding ai. Then if I substitute a equal to 0 and b equal to pi by 2 itself, then I'm getting the same thing. I don't see any result difference. Okay. Same thing I did it for other integrals also. So that's not a problem at all. Okay. So you have to be little thinking is required here to make the changes. That's all. Okay. See, this equation, okay, is same as what I have here. This substitution that I'm just making the x is equal to this. Find the u. So the transformations are perfect. And that is why the change which I made it here. And replace the x by RT of I. That's all. A plus half b minus a x plus 1. Okay. The integrand with this change, it is transformed to equivalent to the u variable from x to u variable that has been taken place. That's what it means. Okay. I hope it is clear. And 1 plus
Sir,
x.
you converted the polynomial to the actual limits.
Polynomial to the actual limit. That actual limit with this transformation, because I see 1 plus of x and you see x is replaced like this. That's what I've done it here. I'm trying to show here. This x is same as what I have. A plus half b minus a x plus 1. A plus half b minus a x plus 1. Got it?
Yes, sir.
This x is replaced with the root. That's all. I retain the limits as it is now, because that will take care of your converting this 0 to pi by 2 to -1 to +1. This transformation. People what to do, they will try to change the variables and put -1 to +1 and then make a substitution that is equivalent to this only. Okay? They are one and the same. They are one and the same. Because that transformation, you need not write it explicitly. You're converting it to -1 to +1. That will be taken care by. See, I am replacing x by a plus half b minus a x plus 1. That is the change. That is equivalent to u. Okay. You can see here. That has been get converted into u. Then you have this b minus a by 2 also automatically will contribute, because you are going to find out du, no, or a dx. Correct? You are going to find the dx?
Yeah.
That dx is when you substitute b by a, it will be there, b by a by 2. So that's how these things have been happening. Okay. So I think this will be carefully you have to follow and then understand it. Then things will be easy. By the process, now it will be easy. You don't have to struggle for every time converting the integral -1 to +1. Retain as it is, just make a transformation here within this x, whatever you have. Then substitute these same limits, because the transformation is accommodated here. Is that right? That's how it has been done. All these two integrals has been done like this, and this already you have -1 to +1. You don't have to worry about it. See, there is no transformation is done here. Did I do anything? Pi by 4 or 1 by 4 pi 1 plus of x as it is, because it is. So every integral you don't have to bring it in this form and then substitute. Not necessary. That is the point which I wanted to make. Even if it is some other root also there, you just make this transformation and bring it into the function, and then make the same limits, you will get the result. That is the point. Okay? I hope it is clear, and maybe you can go through it and make sure that yes, that are consistent. Otherwise, you can substitute them and then make a transformation. Again, you find that it's going to be -1 to +1. Then this will get changed into this form. And then you have a, instead of dx, I have a du. That is what we'll be having it. At that time, you just directly substitute for the x and then make a simplification. Because a and b already has been all substituted with all these limits. Okay, it's fine. I hope this You have to grasp this idea a little bit by spending your time. Same logic can be followed for the other things also. So go to the logger, Gauss, Legendre is over, Gauss Hermite. Okay, this is again we are going to introduce to the new kind of this is your differential equation. It is equivalent to writing this y double prime minus 2x y prime 2n by fx. And you can see the Hermite H is the polynomial which is available. Or which is available. I generated the 10 of them which is available in Mathematica as a Hermite H. Table them up to 0 to 10. I have taken the 11 for 11 values of n I have taken and I have shown this is number 1 for n equal to 0 and then 1 when it is n equal to 1 there is 2x and then minus 2 plus 4x square, like that it goes on. And when you come to the 10 you have it in x power 10. So this is so special about this Hermite polynomial. As I said again, this is differential equation, different kind of an equation that will be again satisfying with the Hermite H. Define that, and the derivative can be taken. Double derivative also can be taken. Substitute, get a solution, and then simplify, which satisfies this equation. And make a plot of that. At least 3 or 4, whatever you like. 0 to 4. 4 of them are already been plotted here. And what about here? If I increase the limits now, how does this function going to behave? So this is also going larger value when you go for a higher magnitude of x now. Because they're all polynomials which x square, x cube, x power 4, like that it goes. Therefore, it becomes huge numbers of powers with an oscillator, some places oscillator, and you can see that it's crossing here. This is also crossing here. One root will be there, and this is two different places, and this is cutting it here also, here and here. So like that it happens. So we are looking for the again weight function, okay, and the root. This is the root, that this is the weight function, and then sum it over by substitution. So only thing you need to have a e power minus x square as a factor here, which means all the integrand you should have an e power minus x square. Okay, those integrals that can be integrated. Now let's see. So I think this is clear. This is nothing great. Whatever if you have done it for Legendre, repeat it, you will get it. This is the n values. Now find the root. I have taken 14th order polynomial, Hermite polynomial, Hn 14. Then find the root of that, and all the roots has been found. And then this is the weight function that is there. So you can see the combined weight function dot. Okay. This is for the n14. Maybe you can check there are 14 of them there. So let's do the integration of e power minus x square cos of. See, similar to that, you are going to add the weight function plus x is replaced by the so-called the root of this Hermite polynomial, and you need to have e power minus x square along with the integrand. So let me first evaluate this. This is the number. This is the function e power minus x square cos x, which can be written this form. Numerically can be found. And see, I am not retaining this e power minus x square. That's a part of your integrand. So it is only enough to have a cos x, because this e power x minus x square is a sort of a weight function for the Hermite. Hermite polynomial has a weight function of e power minus x square. So you can see when I go to the next integral, see, I think this is done here. E power minus x square is not here, only dt of I cos of RT I. So n takes a value 14 here, and as I said, you can change this number. You try here, for example, 5, and see the roots. So I think I have to start from the beginning. Okay, I have to start from here. Evaluate this first, and go to the solution. Solution satisfies. Plotted them. Function is defined, and the root we are going to find. Weight function has been found. Tabulated for how many? N equal to 5. Okay. Then if I sum it over here, okay, 1 point, almost you have reached this accuracy of the 5 decimals. Okay. Suppose if I add 8, maybe a little bit, you have to compare with this, other decimals what you have here. Then you have to check whether they make sense or not. 388. So sometimes this is these numbers we do not know. We have to cross check it with this 38039, 38039. That's what we get it. Suppose if I improve it for them, make it 14. Well, we have 14 roots now. And I'm going to check. That's going to be. But not much improvement. So this is the, and of course you can see that maybe with the limit of say about 8 or 7, sometimes become better. Because sometimes it creates large number of weight function also. Okay, I think this is seems to be better with 5. Yeah. So maybe you have to see other numbers generating here. And I don't know whether it can be possible here. You write it as a number form. Anyway, yeah, number form with the 15 digits is possible. 16 digits because of e power. Wow. Okay. So I have to add n to get the numerical value. Okay, this seems to be right. When you go for a higher value, this seems to be very much agreeing with the 3888447. That's this is accurate value. Okay, up to 19 digits, or you can have it up to 16 digits. Fine. Now, if you want to go for an improvement over this, then you have to go for the 14 terms of the polynomial now. Then look for this value, which is, that's fine. You have come to this almost. Am I right? Are you able to see the improvement? Quite fantastic. 380, 38847, 3114. In fact, this can be written as 3. Okay. This is how it is being done. Now you can see this. There is another integral e power minus x square plus 1 by x square, and limits is from minus infinity to plus infinity. And also see the infinity limits here. So Hermite function can accommodate the limits with minus infinity to plus infinity up to with the weight function e power minus x square. Now I'm going to see this e power minus x square plus 1 by x square infinity. This is square root of pi divided by e square. That's the number, and this number you can get it. When I do this with the Hermite polynomial, I should remove this part of weight function e power minus x square because that's a part of your method. This is a requirement. Okay, weight function that I'm not going to contribute for the calculation, and e power minus of 1 by x square. That is the weight function that I'm going to add. And this is equivalent to integrating this function from minus infinity to plus infinity, e power minus x square plus 1 by x square. So now I'm going to find out this number. For number, how many number of terms? I have 14. The same 14 can be retained. Well, just check it now. Oh, so here, integrate, and I can write this in the form of a number form. We can add, close the bracket, put it in the number form, and add the number form here. Just cross check how accurately one can do this computation. And have a 16 digits accuracy. I have a 16 digits here. Well, is this really coming closer to that? No. Oh, so large difference. Well, you have to check again. This 14 terms have been taken here or not. So this integrand 1 by x square, do the sum up to 14 terms and 2, 4. So I have 1 second decimal is an error. So I do not know whether to reduce the number of terms or increase the number of terms. Or let's take from 8 onwards and see whether it's going to be very bad or it's going to be good. Where is it? E power. This is the term which I'm supposed to sum. Oh, so which means it may require a large number of terms. That's what it means. So maybe I can have a 25 terms that can be taken for this. See, check whether that can improve. Well, I hope that there will be some improvement here. No? Oh, so infinite expression 1 by 0 encountered. So let's really see this problem with this because of this wave function. And the root, there is a 0 sometimes goes and sits there. 1 by 0 is infinity. There's going to be a problem. So these things should be taken care now. When is it you are getting? That's why it is 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13th root has become 0. Suppose if I make 26 even numbers, odd, fine. See how much one has to look into this. This is fine. Yes. Yeah, even that's. So you can, this is the typical behavior of e power minus 1, e power minus of 1 divided by x square. It's going to be a problem to evaluate, and you can see even with this large number of terms, the root becomes bad. So the integrand behavior is completely different with even with this so-called the Gauss-Hermite technique. So this function should be carefully analyzed because you can see the error here in spite of taking 26 terms, and maybe I will try with the 8 terms and then see what is happening. Now 0 roots. This 0, then it's going to be an infinity. There's going to be a problem.
So that is coming from the exponential.
No, there is a root which is passing through the origin, the curve which is passing through the origin. There is root equal to 0. That root, when it comes here, no, e power minus, okay, 1 by of 0 is e power minus infinity.
Okay,
then
there it is.
And then that should be taken care properly by taking the proper number of decimal points. This is again, see, this Hermite method is struggling to come closer to this result, which is the exact result. Okay. So this is our even number I have taken. Suppose See, sometimes you will see, suppose if I take 100, I expect that there may be, see, the root itself is a problem. So we have to check now, start with somewhere about 30, I'll try. That the roots are there and now them become 0, and then we try to look for it. Well, something will come out properly, seems to be 0.239764. I'm able to feel that there is a third decimal 9.8. Okay, third decimal. Fourth decimal is different. 8 you are getting difference. So that this is how we will be looking for this method. So this is what the possible way to look at the result. Check. You can see the weight function values, the initial things. And here most of the roots are negative sign. There's a positive sign. And contribution is very less, only in between this. Okay, so that then you look for the solution. 987, that also is last. So it doesn't mean that when you go for a higher value of the polynomial, your result is improving. So therefore, that should be taken care when you are analyzing this. These possibilities will be limited when you try to do with the fortran, where you don't have an option for immediately changing the number of terms. So you have to really have all the roots ready-made with you, then you have to substitute. This is what really happens. So, okay. So now we can think that there is a possibility that there are certain function, it is getting complicated to get the accuracy what you want because of the nature of the function. Okay, now here is the minus into plus into e power minus x square 1 by square root of x square. This is the, if you do that, it is a special function, special k 0 half. And you find out that number is this. And then here your e power minus square is a weight function. You leave that and do the summation over that. And what is the number of terms that you have right now? 30 terms are there, 30th polynomial we have, 30 roots are there. And we'll check whether this is going to give a proper result or not. Now it seems to be fine. 52411. Probably this is right. Okay, so this is reasonable when compared to the previous one. Maybe here we will reduce to 15 and check. I will reduce the half the number now. Look at this. This one more 0 is also coming here as a root. Well, this is the sum. Check. 52411. 4, 1. Okay. There seems to be improvement, but better when compared to the previous function. If I take 20, come back to here, check. Okay, 4, 1. Greater than. So it's about 4 or 5 digits accuracy is possible now. 5, 2, 4, 1, 1. 5, 2, 4, 3, 4th decimal 1. Okay, that is the order on which you are able to see the roots now. Suppose if I make it about 6 only. And what could be the case with the 6? Seems to be weight function already started getting reduced enormously. 5 to 0. So I think there is definitely there's an improvement when you go for a higher value of number of polynomial now. So this is what the result that you have. Anyway, fine. So now again you can see that this is a simple technique again, but please remember that don't forget to take this weight function into consideration. If you have e power minus square in your integrand, you just leave that and then perform that. Okay. And also here it's an advantage of numerically evaluating this integral minus infinity to plus infinity. That is the big advantage with this Hermite. Okay. So now this is the polynomial which we have seen. It's the generating function. Orthogonality can be seen. Okay. And we have this weight function with this Hermite. What is that here has been done? This and this. Okay, this normalization is being normalized by the, because these two are equal and we'll bring this on the other side of it, will become normalized. Well, you can have the orthogonality here and recurrence relations of 3 different types. Okay, as I said again, this is available in detailed way and with some applications. And I am sure that Hermite, where do you use in quantum mechanics? Hermite. Any idea? No? It is very much used in your quantum mechanics. Well, go to the quantum harmonic oscillator. Okay, Hermite polynomial is the playing a major role with weight function e power minus x square. That's what your starting point, and the ground state has all the properties that is expected in terms of wave packet features. Okay, all this is a Gaussian, no? E power minus x square. So you have uncertainties. All this can be studied for the ground state of the hydrogen. I'm sorry, harmonic oscillator. So this is completely different when compared to the previous one. The next part is, anything you want to learn about this further? Any clarification? After going through this, best thing, as I said, go through the ARFCAN, take out, try with whatever you wanted to understand. It's very easy, and you don't forget about this polynomial. And he has also described its application for the quantum harmonic oscillator. Here discussed, and we have in a separate in our quantum mechanics course. Next is another polynomial, which is also most important polynomial. And I want you to tell, where do you use this logger? This is your differential equation for the logger. X t square by dx square 1 minus x dy by dx plus n by equal to 0. Logger n comma x. This is the logger polynomial. And again, same idea, but the difference is you have a weight function e power minus x. Here you have e power minus x square. So integral of the form in the previous case is e power minus x square of f dx minus infinity to plus infinity. Here it is 0 to infinity. I think this information I didn't write here. Okay. This is e power minus x. This is the weight function, and the limits are 0 to infinity. That can be written as a f of x I. So this is an additional thing that should be available when you do the integration with the limit 0 to infinity. Now again, polynomial, we have the differential equation. Other polynomials available, already defined. Check it, satisfies. You have this polynomial, and this is what your so-called plots. And I don't know what will happen if you plot this minus 3 to plus 3. What happened? Any idea why it is not accepting the minus now? No plot is shown. Any guess? So this is n value. Minus is not allowed, maybe right? And x, suppose if I take minus 4 to plus 4, it's not a problem. It cuts at this place, goes on the both the sides. Okay, it's not an issue at all. It's plotting. So you have the 1 and 1 minus x, and then half of this and 1/6 of the x cube, like that is going on. So it's not a problem. So now we can see when I plot it, I immediately start thinking about what happens to its behavior, extremes. And suppose if you have only my negative numbers, what happens? Is there any meaningful information that can be obtained? But also, we started looking at it now. So now we can see for 0 to 3, there are 4 of them. All the 4 has been plotted here from -4 to +4, and they are all crossing here, and there are crossing. But on the left hand side doesn't cross. You get the point? You're able to see that. Whereas it's crossing here. Suppose if I add one more here or two more counts, 5. Again, this cutting takes place, crosses only this side, not on the other side of it. So this is something very specific, very interesting behaviors. So if I make a plot 0 to 4, we will be able to see that it crosses here, 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 and here. Whereas if I make -4, -4, comma 0, well, I don't think this crossing anywhere. Okay. So this has certain implications that you can think for this logger. Where do you come across logger? Logger polynomial. So we have seen Hermite, Legendre, associate Legendre. They are also available in quantum mechanics. Logger, where do you come across? Hydrogen atom?
Harmonic oscillator isotope.
No. Hydrogen atom, radial part.
Radial part, yeah.
So Logger polynomial, hydrogen. Yeah, any other place?
Wigner function, I think.
I think there are many other places like scattering studies, quantum mechanics scattering, there is a Logger polynomial. And also you'll see Bessel also. Bessel equation, Bessel solutions. So this is mostly, we are exposed completely on the Logger radial part. So it's more meaningful from the 0 moving away from the 0 coordinates. Negative doesn't make sense. So the Logger has that features, and you can see this with the weight function e power minus x. It will become a radial part of the hydrogen atom, solution to the hydrogen atom. So now we are going to, without weight function, but we are going to use for integration of the weight function, and then we are going to see that in the integrand, if I have e power minus x, 0 to infinity, anything available as an f of x dx, that can be done by taking the logger, find the root and weight function, sum it over, you have the result. That's what it means. It's again same. Nothing great here, 14 terms that are available here. Okay, so we can check this is satisfying here. Yes. Simplify equals to 0. Plotted here. Function has been found, plotted here. Now we are going to find the roots here. And weight function is also available. Then find out all the 14 of them for the blind polynomial. And it suddenly goes much faster rate to from 0 into minus 19. Weight function contributions are more towards the lower values of n 1, 2, 3, 4. Okay, so now we have another way to get this function dt. They are not the same. Yeah, that's what I said. There is number of ways one can find out what is the weight function. This is one way to get it, and this is another way. I think the similar thing which we have seen with the previous two. This is another way to. They are one and the same. You don't have to worry about that. But it is because you have the recurrence relations can also lead to that. That's what it means. You have the recurrence relations that are also can be combined here. Then you can possible to see that it will get the same weight function as what has been observed in this. You can see d of this square of that substituting r of t gives the same number as what I have here. That's also same number. Check it now. The numbers what here. So now we have e power minus x square. What you have to do? Integrate from 0 to infinity. Magnitude is half. When I do that with the Logger polynomial, this weight function I will not be considering here, only cos x. Then weight function into this, substituting the weight function value and the cos of x replaced by the root of that, I have a result. That is what the number is. So half is equal to 0.44. Again here, similar integration like what we have seen the x square, e power minus x 1 by x. That's okay. So this is the number. Here I am just removing this e power minus x and perform the integration. I have this similar situation. You can see this fellow struggling to get even improvement over this. Second decimal also this could be a problem. And e power minus x plus x square, error function, great. And this is the number that you have. That number, we are coming closer to that. Okay. E power minus e power of minus 4 minus x plus x square dx. The RF C, not RF. And that can be evaluated. You can see the numerical value to that. Okay. This is fine now. I hope this is clear for all of you. Maybe you can manipulate your number of terms that you require as a polynomial which you already tested. Then see that whether there is an improvement over this computation aspects of that. What is that? Oh, see, sometimes such silly mistakes can happen. N equal to 20. You get the number. This number also possible to get it around the same. Then this should improve now, probably. No, it's not 0.455, 999 you are getting it. Hopefully this should improve. Yeah, it's improving. So it has become 0.27967. So 0.279. From here onwards, there is a difference. So this seems to be a little better here. And what happened to the error function here with the higher orders? Yeah, this is also improving, yes. 6 after this 4 also has 5, 6, 4, 1. Instead of 4, 1, I have 5, 4. This difference. So you just manipulate your numbers and then see what can be done. So this is your Lager polynomial and generating a Rodriguez formula for the Lager polynomial. Okay, the same as that of the polynomial. And you have the normalization that can be found by using this recurrence relations. Okay, 2 different types that has been shown here for the Lager. That is the how we do the numerical integrations. Okay. So that seems to be very good to learn about the special function, and at the same time it will be useful for what? For your numerical techniques. Okay. This is happening here, doesn't matter. So what is the next part of it? We can go ahead with 15. This is something I wanted to show in this. Shall I spend some time here? It's another 15-20 minutes. Maybe I may require about one class about Dell operators and application physics. Shall I spend some time on this, or you wanted to have only numerical? Chinese around? No. Okay, so I'll just close this one and come back to this one more. It's quite interesting. Numerical methods. So you're all familiar with these Dell operators, okay? Maybe I'll coming back to this Dell operators and applications. What is this Dell operators, and how do we understand them? Okay, that's what this going to demonstrate here. And this you might have seen in the Griffith textbook. Okay, ordinary derivative. There's a gradient here. That gradient is defined like this. Okay, this is the Dell operator. This is a vector.
Sir, I was just outside for 5 minutes. That is why I could not answer.
Okay, okay, doesn't matter, doesn't matter. So
Sir,
what I'm trying to
actually,
say.
this part are very important. Even
Okay, that's why I felt
yeah.
that this should be exposed to the students, because they have a difficulty in understanding this so-called electric and magnetic fields, and then the Maxwell's equation visually to feel in a 2-dimension, 3-dimension, and 1-dimension, which can be made now. Visually, one can feel it, and what is that we are trying to do with these del operators, and what the del does, because del is there in almost every part of our physical science. And in physics, almost all the subjects we have the del operator. Okay, you name any topics that you have, the del will be playing a role. And what is the del operator is, and then we try to see how this is being operated and the various situation, and that's being exploited to extract. In fact, whatever which you are trying to do on differential equation is the del. It's only one dimension, which I call it as dy by dx, which is the so-called the derivative. Okay, you can see what is the meaning of a derivative. df can be written as, please note, df by dx into dx. Geometrical interpretation means that the derivative df is slope of a graph of f versus x. So this is the geometrical interpretation. The derivative is a slope which is proportional to the dx. Okay, this is the proportionality factor. Okay, so this is the slope. So this is how we will try to interpret it now. Then, when you have this in 3-dimension, this is what you have. Okay, because it's a function of x, y, z, we'll make it a partial derivative. 1-dimension means we stop with the definite. We just take as a df by dx, whereas here dou t by dou x, dou t by dou I, dou t by dou z, dx dy is the change along the r vector r x, y, z. Okay, this is the derivative. This is total dt, change in t, dt. This is the partial along x, partial along y, partial along z, and the dx is multiplied here for this for dy, dz. We write this is as a dt, which can be written as, see for example, this are going to be here, dx, dy, dz with the x cap, y cap, z cap. This is a dr vector. And we can also write this is x component, y component, z component. If I combine this, I'm getting this dt. Therefore, this is what the function that you have in which the del is operating on a scalar, converting into a vector quantity. That's what it means. Gradient del t is a point in a direction of maximum increase of the function t. When I take a gradient of a function, the del t implies, gradient del t implies, what is that implication? Del t points in the direction of maximum increase of the function t, which means there is a t which is changes x, y, z. Then is where, at what point where the maximum changes that are taking place, that is being picked out by del t. Okay, so this is slow variation. D or df by dx is small, so the df is large. Okay, which means slope is large. df is proportional to the slope of that. You can see that's what the meaning of that. You can see the proportionality factor here. That we are going to extend it from 1-dimension to 2 and 3-dimension. And then when you combine these two, this is what you are getting it. And this is like an operator operating on the t. We call it as a del operator. The magnitude of del t gives the slope, rate of increase along this maximal direction. This is very important for you. So gradient points in the direction, okay, of a maximum increase of the function t, where this t function which is a scalar getting converted into direction, where there is some magnitude also involved and direction also involved. When I take a gradient of a scalar that get converted into a vector quantity, and the magnitude gives you the slope along this maximal direction. So that is the meaning of a gradient here. Suppose I have a function which is a function of x and y. This is x-axis, this is y-axis. I am plotting this function, which is going to be f of x, y. Function is along the z-axis, which is plotted, which is a function of x and y. So the scalar function f of x, y is represented by a surface in A. This is the scalar function. Okay, now I'm plotting this one. Let me take a typical example of this f of xy. For example, f of xy 10 times this 2xy minus 2xy minus x square minus 4y square 18x 28y plus some functional form you can select. I'm going to plot this. I'm getting a surface plot of this f of xy. XSL. F of xy, what does it mean? This is the surface plot. I'm varying the x for a given y. Go to the next y, change the x, next y, and I have a surface plot. This is what the surface plot. Okay. Right. So now you can see there is going to be a combination of x and y that is being taken in the z-axis combined form that we are showing it as a surface plot. Now, if I look at this surface plot, you're able to feel the three-dimensional feel of it, and corresponding function you can see that f of xy, which has some magnitude, and somewhere you can see these slopes are different, not every place, right? At the same slopes are different, not different places.
Yeah. Everywhere.
Everywhere it's getting changed. And if I do a gradient operation, what it does, what is the meaning of a gradient which we have learned? What is the gradient? It has to gradient Dept points in a direction of the maximal increase of the function t. The t function is like this. This is what your t function. Okay. Maximal where it happens, that should be picked out if I do a gradient operation. What does it mean? I'm going to take a grade. You know what is a gradient? This is your gradient. This is what your gradient is. Okay. Del. I'm going to combine with this. I get an x component, y component, z component. So dou t by dou x, which means I have a x and y two variables correspondingly. I'll just take this dou t by dou x and x component, dou t by dou y, dou t by dou z. Because it happens in function of x and y, I find the gradient is 10 is common factor. I'll get the first part of a x component of a vector is minus 18 minus 6x plus 2y. You try this and you get your function by yourself. Confirm it, yes, this is really happening. This is your x component, which is a vector because I can put it in the curly bracket, which is a list, can be treated like a vectors now. First quantity is an x component, second component is the y component. And of course, z component we don't have. Therefore, there are two vectors are there. By taking a gradient, the z component equal to 0. Now I'm going to make a vector plot of this for a different x and y, which means this is the scalar that is being converted into a vector. And vector, what is the meaning of the gradient? It should point out, what is that? It should point out. It should point out the gradient Dept points in the direction of maximum increase of the function t. I'm able to see that pointing out all will be coming towards this, towards this, towards this, towards this. This is seems to be the maximal change that's going to take place somewhere here. Okay. And that I can pick out easily by, you know, what is the method to find a maximum of a given function. How do you find out maximum of the given function? How do you find out maximum of a given function? Easy. This is x and y. What do you do? Take a derivative equal to 0, solve it, you get an x and y. That's going to be maximum. Is that right? I'm going to do that. See, gradient has been found. Okay. See, I'm equating to 0, I'm equating to 0, and solve for x and y. I'm getting x is equal to -2, y equal to 3 seems to be the maximum value for this function because I'm solving this and found out. Okay. So now if I look at the gradient of the field form, in the field, I find, say, 3 minus 2. This is x and y. That's what the plot. X. This is my x and this is my y. -3 to 1, 0 to 5. And you can see this y 3, -2, all of them are getting focused here. Okay. Maximal has been available here. That point has been picked up now by the analysis of the gradient carefully. This is the function. I analyzed it and look for the solution to that. X equal to -2, -3, where you find 720 meter or a feet is the magnitude of that at that point. That can also be checked. So somewhere about -2 plus 3, this is x equal to -2, this is 3. At that point, its magnitude is something like 720. That can be felt by looking at this maximum somewhere. Okay, -3, I'm sorry, -2, this is y 3. Okay, see here, it's here, -2, y equal to 3. That's going to be the solution to this, which I have found it here by even solving that. See. Okay, at that point, you have a slope maximum, tangent is maximum. That is the job of this del t. Speaking of that, it has been done. It's happening here. Maybe if I make it as a vector plot, you are able to see this getting focused there. Make it as a stream plot. A stream also is equal to vector. STREEM probably. Stream. Stream plot. Well, you can see here. 3 minus 2. That is the point. Okay, so now you are able to see that. Shall I take that? This is a vector now. Gradient is a vector now. Am I right? I can make a
Yes,
plot
sir.
of this also.
Yes, sir.
Find by plotting it as magnitude. I can see that place also. Okay. I can look at that point. You can see here. -2 plus 3. That is the point. It is here. This is by plotting the ABS or a norm of that vector is going to be here, and it has a magnitude of a particular point. It has a magnitude that is going to be the location of your this point, which is here. Okay, I have shown both together. Where the function is plotted, and gradient actual value is found, and there is a point at which -2 plus 3, this is the point where the slope is, gradient is maximum, that is being picked out by that. You can see here. This is the surface plot, including both the function and the, after finding the del t gradient, then take that vector magnitude and plot it. That is being picked up here. So this vector plot, what we are trying to show here, its magnitude is like this, like this. Okay, I hope it is some extent it's clear. Please try to understand and go through this problem which is given in the text in the Griffith. You can select any function. It is equivalent to see height of a certain hill in feet is given by this, which is a scalar quantity, where y is the distance, okay, in miles or whatever you like it, north. The x is the distance east of south. Some place is given. Doesn't matter for us. So h is function of x and x, y. This is the scalar. And what we are trying to do by analyzing this carefully with the gradient, you're able to get so much of information about this scalar function without going to any place. Okay, you are able to locate where is the place where it has a point that slope has a maximum value. This is the point. And at what point we are able to locate. Its magnitude also found. This is the height, the direction, everything is fixed. You see how potential is this mathematical operations by just scanning the x, find out what is the heights at the landscaping has been done like this. From the landscaping, you can find out which point has a maximum slope, what direction, what height, all are available. That's the power of this mathematical function. Such a wonderful operator that we have. It's a vector quantity. Okay, and this is purely landscaping and understanding the landscaping. Go to hill station, you might have seen ups, downs, and everything get varies from place to place. But here, if you have an idea about the x and y variation with respect to the sea level, okay, and then you can locate. You don't have to climb up. You just need to have only the height at the different points. Okay, that can be used, and you can play around and get information about all the landscaping that is there. So that is the power of that, and you can see the field now, vector fields. So this is what we're going to use in number of places. For example, here we are going to have this very famous things, divergence, very important for us to understand. And we have a curl of that. Okay, divergence and curl. And then you have fundamental theorem of gradient, how that is being used here to find out the integrals, which we are struggling now. You can see here, this is the most exciting thing. Okay, gradient dot dl, the magnitude depends on the value of the function at the endpoints. So we will spend some time in the next class. And then you have a typical example we try to work it out, which are all given in the Griffith solved problems, but we should get a thorough feel of that. What is that really happening with respect to this? This is the path integral. Okay, we are moving on the path. Okay, del t dot dl, and it is only function of the endpoints. There is a good physics also lying here. A lot of physics which goes into this. And he has given it already, some of them. Is independent of the path taken here to be closed paths beginning to end, identical, hence this goes to 0. So these are all some of the useful informations, the function that is going to happen. Then divergence. Similarly, you have a Stokes theorem, which is using the curl of that. Fundamental theorem of a curl. That's awesome. These three we can spend some time because they are all very often you would come across and you can physically see them, you can feel them. How does it really works? And what is coming out, divergence from a volume to surface, and then line to surface, all this that can also be learned. So I'll stop here, and maybe I have to spend another hour to explain these things and go to the next numerical technique. Maybe what is the next? You can go to the curve fitting. That would be better. Okay, and what about this eigenvalue, eigenfunction, curve fitting? There are some more important things that are there. Okay. So, any questions? Any clarification is required. I'll send this also right now so that you can have a look. Try to have some understanding before I explain. Okay. Any doubts? Any clarification? Is it okay now? I hope.
Okay, sir.
So
Yes.
Shahin is around or he left somewhere? Okay. He must have gone for somewhere. So we can close the meeting and we'll meet tomorrow. Right? I'll send these things to him. He will share with you people. So start.
Okay, sir.
Fine.
Thank you so much, sir.
Right. Bye. See you in the next class.
Bye, sir.
Bye.